Okay, second part of our time spent in 3.5 on implicit differentiation. On the first video, I explained how implicit differentiation is really just a corollary to the chain rule. Okay, because when you're taking the derivative of something of one variable with respect to a different variable, you have to take into account the implied relationship between the two. Let's go ahead and jump right in with another example. If I have x squared plus y squared minus 4x plus 6y plus 9 is equal to 0, and I want to differentiate implicitly in order to find dy dx. By the way, they may occasionally ask you for dx dy just to trip you up, so be careful with that. It would of course just be the reciprocal. Now, if we're going to go ahead and differentiate implicitly, we can go ahead and do it term by term. But as I've always tried to emphasize with y'all need to stop and think before you do. This one, of course, is going to be a little bit easier if we go ahead and arrange it, because this is obviously another circle. So if I put it in terms of a circle's equation in so-called standard form, I need to go ahead and complete the square, and this winds up being x minus 2 squared plus y plus 3 squared is equal to 4. Now, I would rather differentiate this than differentiate this. Okay. Now, when I go ahead and differentiate this whole thing, we could do it, both sides, because remember it is an operation. I get 2 times x minus 2 plus 2 times y plus 3, but I need to take the derivative of the inside, right? Because I am differentiating with respect to x. And x and y do not agree, and therefore y's implied relationship to x must be taken into account. And this is really bad notation, the d dx following the 4, but I just didn't leave myself enough room so you sort of understand. And so this winds up being a much, much easier way than doing it term by term up here, because then you'd have 2 dy dx's, you'd have to collect terms and all sorts of garbage like that. This winds up being actually pretty easy, because I'm going to basically ship this over to the other side as negative 2 x minus 2, and then I'm going to wind up dividing by this expression sitting next to and being multiplied by the dy dx. And therefore I'm going to get 2 minus x over y plus 3, and that right there is probably an easier way to go ahead and get at the derivative dy dx of that original circle equation. Okay. Now we can go ahead and go through, and I'll let you go ahead and do that on your own to find the derivative if we were to do it term by term from its original polynomial form. But let's go ahead and move on. We have x squared minus y cubed is equal to, let's go 0. And I want the equation of the tangent line at 1, 1. Okay. Now you have your computer with you, so you can go ahead and graph that if you would like. But I need to go ahead and confirm that 1, 1 is on the curve. If I plug in 1 into x and 1 into y, I get 1 minus 1, and that's 0. But I want to know the derivative at that point, such that I can actually get the equation of a tangent line. If I want to differentiate with respect to x, I get x squared minus y cubed is equal to d dx. And of course, like I've said before, you don't have to do this step. I'm just trying to, because we're still relatively new at this, trying to emphasize the fact that it is an operation, and you're doing it to both sides of the equation. So you have 2x minus 3y squared y prime, and of course y prime stands in for dy dx, is equal to 0. And so y prime is equal to negative 2x over negative 3y squared, and we can go ahead and cross out those negatives, and we wind up getting 2x over 3y squared. Now that means that if my y prime is evaluated at the ordered pair 1, 1, I'm going to get 2/3 as a slope. So the equation of my tangent line comes from both the slope and the point. So I have y minus y1 is equal to m times x minus x1. That is the equation of the tangent line. And if you want to go ahead and plug all that into the graphing software that you have on your computer, it will confirm the fact that this is the tangent line to that curve at that point. Okay? And I can show you a couple more, and I will here in just a moment. I just don't have that one plugged into Grapher. I have a later one plugged into Grapher. And I don't want to sort of waste our time trying to go ahead and do that right now on the fly. Let's go ahead and do another one in terms of the finding a tangent line. If we have x to the 2/3 plus y to the 2/3 is equal to 5, let's go ahead and do that at the point 8, 1. Okay, and if you actually plug that in, it does work. 8 to the 2/3. What's the cube root of 8? 2. 2 squared is 4, and of course 1 to any power is going to be 1. So 4 plus 1 is 5. Okay, this is one of those asteroids, not asteroid, asteroid, right? Asteroid. It's because it looks like a star. It kind of does that number. Okay, it kind of looks like that. Okay, now we need to go ahead and take the derivative of both sides with respect to x, and we have 2/3 x to the negative 1/3 plus 2/3 y to the negative 1/3 times y prime. And of course, the biggest mistake that I always see is you're going to put a 5 right here. Well, if I've differentiated both sides, the derivative of a constant is always 0. Okay. Now, once you recognize the fact that there's a 0 on the other side, you can go ahead and if there's a common coefficient, you can go ahead and just cross them out, right? And this is 1 over the cube root of x plus 1 over the cube root of y prime is equal to 0. Or y prime over the cube root of y is equal to negative 1 over the cube root of x. Okay, I'm going to continue working on this. And therefore y prime is equal to negative cube root of y over x. Okay. Now, we need to go ahead and evaluate this y prime at the ordered pair, 8, 1. And, I mean, it's the cube root, and both of these are perfect cubes, so it actually ought to be relatively easy. So y prime of the ordered pair 8, 1 is negative cube root of 1/8, or negative 1/2. And therefore, this is your m, this is your x1, y1, and you simply have y minus y1 is equal to m times x minus x1. And you can, easily enough go ahead and put that into slope-intercept form if you want. But like I said before, on a free response question on the AP exam, point slope is going to be good enough. Okay. Now, the last one I think we're going to do, that's maybe the last one, depends on how long it takes us. The next one that we're going to do in terms of tangent line, I'm actually going to show to you. So this is x squared plus y squared is equal to 4x squared y. And I want the equation of the tangent line at 1, 1. Okay? This is actually kind of a famous curve. It's called a bifolium. And remember though that thing of famous curves that I showed you last year, and we went through and we kind of went, ooh, the bifolium was in there. Okay. Let's go ahead and differentiate with respect to x. So if I differentiate this side, this is stuff squared, so it needs to be 2 times stuff times the derivative of stuff, which winds up being 2x plus 2y, y prime. I'm going to have to do the product rule, of course, on this right-hand side, and I'm going to get 4x squared y prime plus 8xy. Now, in order to go ahead and sort of clean this up, I do recognize the fact that I can pull a 2 out of here and join it up with this 2 and make a 4, right? That, of course, will cancel out if I want to divide both sides by 4. So I can, clean it up a little bit. Plus 2xy, okay? Now, what I really need to do here is I need to free up this y prime from that binomial, so I need to go ahead and FOIL. So the first, that's x cubed. Outer is going to be x squared y, y prime. Inner is going to be x, y squared. And the last is going to be y cubed, y prime. And this is x squared, y prime, and 2xy. Now, notice that there are 3 y prime terms here, here, and here. Either way, you're going to have to move 3 of those terms, right? But let's go ahead and just collect the y primes over here on this side. So I know that once I've sort of jockeyed it around, these 2 are going to be positive. This one is going to be negative. So it's going to be x squared y plus y cubed minus x squared is equal to 2xy minus x cubed minus xy squared, or y prime is equal to 2xy minus x cubed minus xy squared. All of that over x squared y plus y cubed minus x squared. And now, to evaluate that at 1, 1. Well, if you want to evaluate that at 1, 1, it winds up being relatively easy. Basically, all of the products that don't involve an extra coefficient wind up being 1, right? So this winds up being 2, and this is not an equal sign. This is basically what it goes to once I evaluate it. And let's go ahead and do it. Y prime of 1, 1 is equal to 2 minus 1 minus 1 over 1 plus 1 minus 1, or it's 0, okay? So if the slope is 0 and it goes through 1, 1, then it's just y is equal to 1. So there's a horizontal tangent line at that particular point. Now let's go ahead and take a look at it. That right there is the bifolium. Okay, let's go ahead and add a new equation. And y is equal to 1. Okay. That right there, and we can go ahead and zoom in just a little bit. Let's go ahead and, that was probably a little too far. We see the fact that right here at 1, 1, we do have a horizontal tangent line. So it actually does wind up working out rather well, okay? My advice to you is the problems that you go through, in order to be able to sort of get a visual on all of this, I really do recommend opening up Grapher, or if you have a PC, opening up WinPlot or something like that, and actually looking at the details of exactly what you're doing in terms of the tangent line problems. I think it will be very, very instructive. Okay, guys. That's it for our second video on implicit differentiation. I'll go ahead and start working on a couple of more. This is just going to be something that it's going to be very, very easy in the long run. It's going to wind up being a habit. It's just not yet, and it's a little bit disconcerting because, you know, implicit equations are never as easy as explicit ones, but you guys will get it, I have no doubts.